We are going to go ahead and get started. We're going to be continuing along this pathway of talking about riparian and water quality and stream habitat. And we have a couple of sets of paired talks in order to do that for you this afternoon. The first will be with Ashley Coble with NCASI, National Council on Air and Stream Improvement. I'm going to be happy with myself to keep getting that right. And Brooke Penaluna with the U.S. Forest Service P&W Research Station. They're going to come up and talk to you about fire and streams. First, Ashley with forested streams, fire and large wood across a gradient of fire severity and forest stand age. And then Brooke about what happens to fish when their forest is on fire. Answers from 24 Oregon streams. And they'll take questions after both of their talks are done. So help me welcome them up. Thanks, ladies.
Thank you. So first I want to start by acknowledging my co-authors on this work, Brooke Penaluna of the Forest Service, Laura Six from Weyerhaeuser, and Jake Verskyle of NCASI. So I'm primarily going to be talking about large wood. So I want to start by talking about why large wood is important for streams and for their function. So depending on the placement of large wood within the stream, it can be functional, meaning that it has the potential to alter channel morphology and also alter flow regimes. And so it can alter flow velocity and increase heterogeneity within the stream channel itself. These are some images showing you examples of pool formation, for example, but also in these cases, then large wood also has the capacity to enhance sediment storage within the stream channel. And collectively, what these can provide areas of refugia for fish and amphibians that can be very essential during certain times of year. Before I get too far, I want to talk a little bit about sources of large wood and terminology that I'm going to be using as we move through this data set. So this is a continuum of vegetation and river corridors as defined by Ellen Wool's book in 2020. So where does large wood come from? It starts as a tree. That tree is live, standing tree. Eventually it dies, it becomes a dead standing tree. When it falls over, it becomes coarse wood on the forest floor. And I'm going to be using the term coarse wood to try to differentiate this wood when it's in the riparian area from large wood when it's in streams. But I'm using the same size class for both of those components, which is greater than 10 centimeters in diameter or 1 meter in length. So to think about what the expected response of large wood is to fire, we can look at Kyle Martin's 2020 review paper on large wood. And here I've tried to highlight in red the expected response to fire. And so after a large stand replacing fire that it affects the entire watershed, we expect to see an increase in the amount of wood that occurs in streams. And so that increase occurs during this stand initiation phase of forest successional stage. Eventually, as you move into canopy closure, then that large wood can get pushed out of the system. And so we start to see a decline in the total amount of large wood in streams. Eventually that returns to baseline, but continues to drop because there's no longer a source of large wood in the watershed. But here in the Pacific Northwest, there's a very complex history of large wood, specifically with respect to historical harvest practices. So it was common practice to remove large wood from streams, as we heard earlier with those BLM examples. So large wood was actively removed, also with log drives and splash dams led to the removal and channelization of streams. And historical practices were to clear cut the entire watershed, not retain a buffer, and also broadcast burn the entire watershed. So as you can imagine, that leads to this trajectory where we're in a situation of having a dearth of large wood, and that was the situation prior to these 2020 wildfires. So we're effectively superimposing this red line of the response to fire on top of this historical legacy effect of large wood removal. So you heard a little bit about this study earlier in terms of the vegetation response, but I'll just rehash the study design a little bit. So we opted to use a stratified random sample of pre-fire stand age and fire severity to identify 24 fourth order watersheds. And we were focused on 3 fire boundaries. So Riverside, Beachy Creek, and Holiday Farm. And we opted to include control watersheds that occurred within 6 kilometers of the fire boundary. So all of these are at fourth order watershed scales. The age was younger than 85 years on average at this scale, or older than 85 years on average at this scale. And the reason that we wanted to incorporate age is we wanted to also incorporate pre-fire management activities that will also influence not only fire severity, but also the aquatic responses in the post-fire recovery period. So initially, first selection, we used overlap with the fire boundary. So we had reference conditions, we have watersheds that are completely within the fire boundary, and then we had those that were majority and minority burned. But for the purposes of this talk, I'm gonna be using fire severity as a predictor. And so the fire severity I'm referring to here is this rapid assessment vegetation condition. And so this is a remote sensing derived metric that estimates overstory mortality. So bright red represents 90 to 100% mortality, going down to blue, which is 0% overstory mortality. And so this is a raster. We were able to average that for the entire watershed. So this is borrowing data from Laura Six, who presented earlier, just to understand what's happening with the riparian overstory. And so we were interested in overstory mortality, but we wanted to look at burned versus unburned riparian areas differently. And here, burned areas are referring to when the riparian zone where we're measuring it had a soil burn severity greater than unburned, essentially, so low or moderate or high severity burns. And what we found is that there was no difference in mortality for species in unburned sites, but for burned sites, we did see significantly greater mortality rates for Douglas fir and western red cedar than red alder. So it was 6.8 times greater in Douglas fir and 5.5 times greater in western red cedar than red alder. We did not see a significant difference for big leaf maple or western hemlock. Importantly, across all of these watersheds, red alder is one of the most common tree species that occurred within our riparian areas. So as we move into thinking about volume of wood, so we're going to start with this coarse wood volume. So this is the wood, down wood in the riparian area itself. And here on the x-axis, we have our fire severity metric. This is that rapid assessment vegetation condition. The key on the top is showing you that condition from 0 to 7, with bright red being the most severe. And then you can also see the symbology for pre-fire stand age with circles representing the younger on average watershed stand age and the triangles representing the older on average watershed stand ages. So what we see with the coarse wood is that we do see a significant difference in volume with fire severity. And so as we move from our reference sites on the left, we have relatively high wood volume occurring. It declines as we move into moderate severity burns and then increases again as we move into higher severity burns. So we're seeing this U-shaped response for volume in the riparian zone. As we move into the stream itself, we no longer see a pattern. So we don't see a significant difference for volume of large wood that's occurring in the stream with fire severity. But next, let's think about size. So in terms of size, we can look at diameter. Now we're starting with our vegetation continuum. So these are live and dead standing trees. So live are represented in green and dead are represented in the black filled circles. There's no significant difference with DBH in live or dead standing trees within this riparian data set. As we move into coarse wood in the riparian zone, we again see a significant response, and it's still that sort of U-shaped response where we're seeing higher, larger diameter wood in reference sites and also in more severely burned sites, but it's lower in the moderately burned sites. And that pattern, of course, was similar to what we observed with volume. As we move to look at large wood in the stream, we do see a significant response, but it's different from what we've seen in the riparian area. And here, we're seeing a significant decline in the size of large wood as we move to more severe fire, or more severely burned watersheds. And so what this suggests is that there's potentially younger fire-killed trees that are occurring only in these most severely burned watersheds. And so this bottom panel is slightly different, x-axis. This is really just to compare our diameters in our riparian zone to in the stream. And so on the x-axis, you have the coarse wood diameter in the riparian area. The black line here represents the 1-to-1 line. And so we would expect, of course, larger diameter wood to occur in the riparian area before it's transported into a stream. But we have 3 watersheds where we actually have larger diameter wood in the stream than what we observed in the adjacent riparian area. And importantly, these are all triangle symbols, which indicate that they're older on average watershed stand ages. And specifically, these are quite a bit older. These are all 115-year or greater watershed stand ages. So this suggests that there is a source of old, larger wood somewhere upstream of our measurement reach, and so the wood directly adjacent to our measurement reach is slightly smaller than what is potentially available upstream of our sources here. But for the most part, what we see is that there's larger wood in the riparian area than in the stream, and this does indicate future recruitment potential and potentially the ability to improve in-stream habitat. So I wanted to focus primarily on large wood for this talk, but I do want to acknowledge that we have quite a bit of other data available. And so I just quickly want to introduce you to how our large wood is relating to all of these other metrics that we know are correlated. So to break down all of our data into fewer components, we used a principal components analysis, and then we took each PC axis and related those to either fire severity or pre-fire stand age. And so we found that fire severity explained the majority of the variation. This explained the variation in our first principal components axis. And what this suggests is that in more severely burned watersheds, we have higher tree mortality, greater light availability onto the stream channel. We have greater salvage, both at the watershed scale and also in the riparian areas. And we also have higher dissolved organic matter concentrations as both carbon and nitrogen. Less severely burned watersheds were more associated with higher overall canopy cover, larger diameter large wood, more macroinvertebrate diversity, and also higher fish density. Our second PC axis, which explained less of the variation in the data set, was significantly related to pre-fire stand age. And so we find that the watersheds with the older on average watershed stand age were more associated with higher elevations and mean annual precipitation and lower mean annual temperature. And so in contrast, our younger on average watershed stand ages were more associated with mean annual temperature, which also is reflected in stream temperatures as 7-day maxima. We also saw higher phosphorus concentrations as both total phosphorus and inorganic phosphate, and then also saw elevated SUVA 254, which is an indicator of carbon aromaticity. And so that suggests that there's greater, more terrestrially derived carbon occurring in these younger watersheds than what we're observing in some of those older stand age watersheds. And so, clearly here we have some confounding factors with elevation and climate that may be controlling what we're observing here. So while we're using pre-fire stand age as this predictor variable, it's certainly encompassing other ownership histories and other factors as well. So to wrap up, so our tree mortality data did speak to that there may be an important function of red alder in these fire-prone landscapes. And that's not necessarily to suggest that it's going to provide a great source of large wood, but to suggest that it's going to provide some shade because it has greater survival in our riparian areas. And so that will limit the temperature increases, at least in the near term following the fires. We also see from our coarse wood responses that it does indicate some potential future recruitment of larger diameter wood and also volume in some of those most severely burned watersheds, at least in the near term. Of course, with this story, we have to acknowledge that any removal of coarse wood from the landscape, whether it's in riparian areas or uplands, is going to influence future large wood recruitment for decades. And so that's an important consideration as we're already looking at a potentially reduced large wood on long-term timescales across all of these fire boundaries. So we worked across landscapes, we worked across ownerships. These are the many landowners that provided access for our study sites. They've provided salvage and post-fire management information. We have quite a crew to thank, both in terms of the field crew and also lab technicians that have helped analyze some of our data. And with that, well, I would take questions, but I think we're going to move swiftly into the next talk.